In this video, we're going to talk about Gram-Schmidt orthogonalization or Gram-Schmidt process. But before we talk about Gram-Schmidt, we first need to know what a basis is, because Gram-Schmidt is nothing but getting an orthonormal basis for a given space. So we first talk about basis, and let us have a matrix A, and we want to get the basis for the column space of that matrix A. The column space of the matrix A is the space that is spanned by the columns of this matrix. The same for the row space, which is the space that is spanned by the row of this matrix. As a first trial to get a basis, we can actually do what's so-called a reduced row echelon form, RREF for short. By the way, this is a command for MATLAB or Octave. We start by a reduced row echelon form. It's an easy task to get a reduced row echelon form, and also reduced row echelon form provide us with a pretty good thing, because a reduced row echelon form tells us what are the pivot columns and what are the free columns. And according to what we see here, we have a pivot here, and a pivot here, and a pivot here. So that means a column 1 and 3 and 4 are pivot columns, which means they are independent, and the column 2, 5, and 6 are nothing but a linear combination of the columns 1 and 3 and 4. So as we can see here, we have a pivot here, and pivot here, and pivot here, and by simply applying reduced row echelon form, we managed to get the independent column. But the fact is we did row operations, and row operation change the column space of the matrix A, but does not change the row space of the matrix A. So to actually get a basis for a column space of the matrix A, then we need to take the column 1 and the column 3 and the column 4 of the original matrix, and those vectors now can be considered as a basis for the column space of the matrix A, while the one in the matrix reduced row echelon form are not basis because we did a row operation. So by this simple procedure we managed to get a basis for the column space of the matrix A, but as we can see here, the bases that we got are sort of arbitrary, that is, they do not cover any special property. So we will take a further step and try to get a simplified basis. Well, to do so, we need to take the basis of the column space of the matrix A and put them as rows inside another matrix, for example B. By doing this, the row space of the matrix B is the same as the column space of the matrix A, since the rows of the matrix B contains the basis of the column space of the matrix A. Now we will get the reduced row echelon form of the matrix B. After doing that, we got a simplified basis for the row space of the matrix B. As we can see here, we have lots of ones and zeros. And since row operation does not change the row space, then the row space of the reduced row echelon form of the matrix B is the same as the row space of the matrix B, which is the same as the column space of the matrix A. So by this trick, we got a simplified basis for the column space of the matrix A. So now we can say that the matrix B transpose has the basis of the column space of the matrix A, while the reduced row echelon form of B transpose contains again a basis for the column space of A, but they are simplified this time, which means you have lots of zeros and 1 inside your matrix. So now we understand what is the meaning of basis and how we can get them. You accept the normal basis that you can get them directly according to the reduced row echelon form, or you take that a step further and get a simplified basis again by using the reduced row echelon form. But sometimes this is not enough, and sometimes we want more. And that's why we're going to talk about Gram-Schmidt. Gram-Schmidt orthogonalization is simply nothing but getting an orthonormal basis. First of all, why they are called orthonormal? The first part, ortho, refer to that those spaces are going to be orthogonal, that is, the dot product between them will equal to 0. And the second part, normal, refer to they will be a unit vector. So now we have two constraints on our new basis, that they must be orthogonal and they must be unit vectors. Now let us assume we are in a three-dimensional space and we have three vectors v1, v2, and v3. Clearly they are not orthogonal, but they are independent. So out of these three vectors, we want to get a new basis with a constraint that they are orthogonal and unit vectors. So we will start with the first vector, u1. So our new basis, we will give them the letter u. We will consider that u1 is equal to v1. Hence, the unit vector u1 is equal to the unit vector v1, which equal to the vector v1 over the magnitude of the vector v1 or the norm of v1, which is again equal to u1 over the norm of u1. So getting the first vector is easy. Now every vector we're going to get from now on must be orthogonal to u1. So we first try to get u2. We know that any vector in a three-dimensional space can be decomposed into two orthogonal vectors. So for example here, v1 is equal to u1, and v2 can be composed to have a component in the direction of u1 and a direction orthogonal to v1. And we will call it u2. Now our job is to get that u2. Well, again we said that v2 can be decomposed into two orthogonal vectors, A times U1 as a unit vector plus B times U2 as a unit vector. But then we realize that A is equal to V2 dot product with U1 as a unit vector because A is a component of V2 in the direction of U1. So to get the component of the vector V2 in the direction of the unit vector U1, then you need to take the dot product of V2 with the unit vector U1. Then again plus BU2. Then we can write this as U2 is equal to the unit vector U2 times B, which is equal to V2 minus V2 dot product with the unit vector U1 in the direction of the unit vector U1. So by now we have U2, and to get the unit vector U2, then U2 unit vector is equal to the vector U2 over the norm of the vector U2. So till now we managed to get two orthogonal bases, which they are U1 and U2, which are orthogonal, and at the same time they are unit vectors. Again, by the same procedure, any vector in a three-dimensional space can be decomposed into three orthogonal vectors. So we can say that V3 is equal to C times the unit vector U1 plus D times the unit vector U2 plus E times the unit vector U3. But then we realize again that C is nothing but V3 dot U1 unit vector, because again C is a component of V3 in the direction of U1, and to get this component then you need to multiply V3 dot product with the U1 unit vector. The same for D, which equal to V3 dot product with the unit vector U2, and then we add E times U3 unit vector. Well, by this equation we can say that U3 is equal to E times the unit vector U3, which is equal to V3 minus V3 dot product with the unit vector U1 in the direction of U1 unit vector minus V3 dot product with the unit vector U2 in the direction of the unit vector U2. And since now we have U3 as a vector, then we can simply get U3 as a unit vector, which equal to the U3 over the norm of U3. So by this we managed to get a three orthonormal bases out of three independent bases, V1 and V2 and V3. And the idea is generalized for higher dimension. So for example, if we are in a four-dimensional space, then to get U4, we will do the same procedure again. We will say that U4 is equal to V4 minus the component in the direction of U1 minus the direction in the component of U2 minus the component in the direction of U3, and this will give you U4, and once you get U4, you can get the unit vector U4. So by now we have U1, U2, U3 unit vectors are orthonormal bases, and they are both orthogonal and unit vectors. Now you may wonder why we want to get an orthonormal basis. The answer is orthogonal matrices, because if we stack those orthonormal bases U1, U2, and U3 unit vectors inside a matrix, then we say this matrix is an orthogonal matrix. So Q is an orthogonal matrix, and it has a really useful property, which is Q transpose is equal to Q inverse. And it is easy to prove this statement. It will only take you 2 or 3 lines of algebra, which is not interesting by itself. Now we know that to get the inverse of a matrix, this is need a high cost. But if I told you to get a Q transpose, then the cost is not that big and you can calculate it easily. So this is really a useful property for orthogonal matrices. Another beautiful property for orthogonal matrices are their geometric interpretations. Because if you were actually making a linear transformation, then the matrix Q will provide you with a rotation. So if you wanted to rotate your space, then you need to multiply it by a Q matrix. So orthogonal matrix will provide you with a rotation. And in fact, orthogonal matrices are either a rotation matrices or improper rotation matrices. And the improper rotation matrices are nothing but a rotation followed by reflecting one of the bases. And this is actually useful if you needed to change the handedness of the system. If you wanted to keep the handedness of the system, then use a rotation matrix Q. While if you want to change the handedness of the system, then use an improper matrix Q. So any orthogonal matrices are either rotation matrices or improper rotation matrices. Our time is up. Thank you for watching.